Hello everyone, Mr. Fawcett back here for part 2 of our lesson on the squeeze theorem. This video is going to contain about 3 to 4 practice problems depending on how much time we have where we are applying the squeeze theorem in one way or another. Note that it's also can be called the sandwich theorem. But before we check out those practice problems, I want to do a quick review of what the squeeze theorem is to give you a quick refresher on what we learned in our last video. So the squeeze theorem. If we have a function f of x, which is less than or equal to a function h of x, which is less than or equal to a function g of x. So basically we have a function h of x that's always between or equal to f of x and g of x. Around a certain point, x equals a. Then if the limit of the f of x function as x approaches a is equal to L, and the limit of the g of x function as x approaches a is equal to L, then the limit of the h of x function as it approaches that same x value, a, will also be equal to L. And again, that's a lot of words, and I think a visual is sometimes helpful in understanding what's going on here. So I put a quick graph down here to the right. I have my g of x function, which is the greatest function of the three. That's in red. My blue function is our f of x function, and I just chose the x value. So in this case, this is going to be x is equal to 1, where they are equal to the same value. Okay, and we're going to call that 3. So if I have a function h of x, it always has to be between g of x and f of x. So you can do kind of whatever function you want, but it's always going to be between the two. And as it comes in from both sides, you can quickly see that there's only one point that the function can obtain at x equals 1, right? Because it has to be between or equal to g of x and f of x. So the limit of the pink function is going to be the same as the limit of the top and the bottom function as we approach that x value. And that's again because it's being squeezed between the top and the bottom functions. At the other x values, they don't have to have the same value, right? Because it's not clear that g of x and f of x have the same values at other points. But specifically at that one x value, where the top and the bottom function come up and meet, the middle function, if it's being squeezed between them, it has to equal that same value as well. Okay, let's try to put this theorem into action. We have a problem down below. It says, suppose f of x or h of x is greater than or equal to f of x, but it's less than or equal to g of x when x is near 2. And then it gives us our f of x and g of x functions. Then it asks us to determine the limit of h of x as x approaches 2. Again, pause the video. See if you're able to come up with any ideas or strategies on how to figure out this limit on your own. Then click play and see if your thoughts were close to my thoughts. Okay, so I got rid of the graph just to give us some extra space. But essentially, what we need to think about here is they don't give us the function h of x. So our only real option to determine this limit is to invoke the squeeze theorem. And they already tell us that h of x is between f of x and g of x, and that f of x is always less than or equal to h of x and g of x. So that condition of the squeeze theorem is already met. But the other condition is that the limits of the top and the bottom functions as we approach x equals 2 have to be the same, right? So the limit as f of x approaches, the limit of f of x as x approaches 2 must equal the limit of g of x as x approaches 2. If those two limits are the same, then we'll know that the limit of h of x as x approaches 2 will be the same as those other two limits. And that's because if their top and bottom function are approaching the same value, then h of x is being squeezed in between them and will also be approaching the same value. So all three limits will be equal. Let's start by finding the limit as x approaches 2 of f of x, which is negative 1/3 x cubed plus x squared minus 7/3. Now again, when we evaluate a limit, we always want to check direct substitution. So if I substitute 2 in for x, I end up getting -1, and you can work out the algebra for that or put it into your calculator. I'm then going to check the limit of my g of x function as we approach 2, which is cosine of pi times x over 2, which is going to be equal to cosine of 2 pi over 2, which is equal to cosine of, cosine of pi, which is equal to -1. I did show the simplifying for the trig function, just because we're probably a little less familiar with that. If we have shown, and we did, so once we show that the two limits of the top and the bottom functions are equal, then we can say by the squeeze theorem or using the squeeze theorem, you just have to mention the squeeze theorem. So by the squeeze theorem, the limit as x approaches 2 of h of x is equal to -1. Now, if you don't use the squeeze theorem and you just say the limit as x approaches 2 of h of x equals -1, you would not receive full credit, right? Because there's no way to show what that limit is unless you use the theorem up above, the squeeze theorem or the sandwich theorem. If you said the sandwich theorem, you would also get credit as well. Okay, let's move on to the next question. Question 2. So same scenario here. We have a top and a bottom function f of x and g of x, and we have a function h of x that is in between those two functions. This time we're looking at the point as x approaches -1. So same idea. Can we show that the limits of the top and the bottom functions are equal to one another? If we can say that the limit of the middle function is going to be equal to the limits of the other two. So let's start with f of x. Limit as x approaches -1 of -1/4 x squared minus 1/2 x. If we substitute in -1, we're going to get -1/4 plus 1/2, which is going to give us 1/4. If I look to find the limit of the g of x function, so the limit as x approaches -1 of 1/3 x squared plus 2/3 x plus 2/3, this is going to give me, and I'll just write it out because this is 3 terms is harder to do in your head than 2. We get 1/3 minus 2/3 plus 2/3. So this gives us 1/3. So while the limits are close, they are not the same, which means there's some room for the limit of h of x as x approaches -1 to be more than one value. So we cannot invoke the squeeze theorem here, and we would not be able to give an answer because the conditions of the squeeze theorem were not met, right? The limits of the top and the bottom function are not equal to one another. Let me just show you why this doesn't work before we move on to our next problem. So we're approaching -1. And we have 1/4 and 1/3. I'm going to space the axes out a little bit, or space the tick marks out on the y-axis just to make this even more clear. I know that f of x is my bottom function, and that limit is approaching 1/4. So essentially I have something like this. I know my g of x is my top function, and it's approaching 1/3. So it looks like this. So you can clearly see that there's a lot of ways I could draw my h of x function, right? I could draw it down there, or I could draw it somewhere up here, right? And depending on where it's being drawn, that limit is going to be different, right? For that bottom pink function, the limit's going to be a little bit less than it would be for this top pink function. But both of those would be valid pink functions because the limits of my red and blue are not the same. So there's a gap, which means my pink function could fit in multiple different spots, and the limits could be different as well. So we cannot invoke the squeeze theorem for number 2, and we can't say anything about the limit of h of x as x approaches -1. All right, let's move on to our third problem. This one's a little bit different. Let me see, make sure I can fit both these graphs on the screen. So the problem says Daniel is trying to figure out the limit as x approaches 0 of h of x. And if we look over at our graphs, the black parabola-looking graph in the middle is our h of x function. He can estimate that it is equal to 0, but wants to prove it. So just looking at the graph isn't a formal proof. It's just a very good way to estimate what a limit is. And if we look at the graph of h of x, well, it certainly looks like the limit as x approaches 0 is going to be equal to 0. But again, it's not a formal proof. So maybe he'll be able to use the squeeze theorem to come up with something more formal. Jessica suggests that he uses the squeeze theorem using the functions f of x and g of x graphed below. So in our second graph, we see the functions that Jessica chose to try to prove the function of h of x as x approaches 0. So explain whether this strategy will work. If it won't, can you change something about Jessica's answer to allow the use of the squeeze theorem? So whenever we see a theorem, right, our initial conditions have to be met. For the squeeze theorem, we have to have a top function that is greater than or equal to both the other functions around whatever x value we're looking at. So in this case, we're looking at x equals 0, so we have to have a function that's greater than or equal to both other functions around that point. It looks like the function she chose to be the function that's greater than h of x and g of x is this green function. Okay, so if we look down at the second picture, as we approach from the left, we see that the green function is greater than both the black function and the red function. Now, you may notice something that is off about this. Maybe it looks a little different. We'll come back to that in a second. She also chose another function, g of x, that's the red function, that looks to be the function she chose to be less than the other two functions. So we can kind of see how this h of x function fits between the green and the red function. Now, of course, you may see the problem. Well, what happens when we move to the other side of the graph, right? All of a sudden, if we move to the other side, now both our red and our green function lie below h of x, which is supposed to be our middle function. So this isn't going to work. This isn't going to, or these two functions are not going to work to help us invoke the squeeze theorem. We have to come up with a function that is always greater than or equal to the middle function around that x value, and a function that is always less than or equal to the other function around that x value. So is there a way to change, right? And it probably makes sense to change the green function because the red function is always less than or equal to h of x. But maybe there's a way for us to change the green function or come up with a new function entirely that is always greater than or equal to h of x around x equals 0. So maybe it'll help you to start sketching, but take a minute or two, see if you could come up with both a drawing and an algebraic way of describing a function that is always going to be greater than or equal to h of x around the point x equals 0. Okay, so maybe you came up with one, maybe you were unsure. It's going to be easier for me to use this top. It's going to be easier for me to use this top graph, so I'm just going to redraw our bottom function. It's not going to be perfect, but it's going to look something like this. Let me get my pen. So it looks something like that. And what I would like to do is I'd like to have some sort of parabola, right? That's narrow, or more narrow, than this parabola shape that we have for our black function. And again, these aren't parabolas per se in the quadratic form. I'm just giving you a general description of what these functions look like. Let's draw that a little bit better so that we can see that it also equals 0 when x is equal to 0. Now, we need to come up with a equation for that pink function, and this is something you can do to just play around in your calculator, right? I'm changing the function f of x. So my new function f of x, I know it's got to be some sort of parabola that's opening upwards. So I'm going to have an x squared. Now, to stretch that vertically, right, to make it more narrow, we need to make the coefficient in front of x squared greater than 1. And the more positive that number becomes, the larger it becomes, the narrower the function. So you could just pick a number, and let's go with 5. And you could test a point. So we could test the point f of 1. F of 1 is going to be equal to 5, which is actually, well, it's not actually close to what we have here. But if I now graph this function based on this point, my point would be here. Of course, f of negative 1 is going to be the same because it's an even function. And my parabola would be very, very narrow. So it would be greater than h of x at every point, essentially. Specifically around x equals 0. Okay, so again, the idea here is not necessarily making you write out the equation of a parabola that works, but it's understanding the conditions of the squeeze theorem. So it's understanding that there has to be a top and a bottom function. Those functions can't switch somewhere around the x value that you're looking at. So if we come down here, right, this green function was greater than h of x, but then it became less than h of x after we switched, or after we passed that x value. And you also have to check the limits, right? If we go back to question 2, the limits of the top and the bottom functions as x approaches that certain value have to be the same. So make sure those two requirements are fulfilled, then you are free to invoke the squeeze theorem to prove what the limit of the middle function is going to be at a certain x value. All right, this is Mr. Fawcett signing out. I look forward to seeing you next video.